So the next is the positive definite matrices. So a symmetric n cross n matrix Q is positive definite if this quadratic form, that is X transpose, where X is a vector, Q is the symmetric square matrix. Symmetric matrix meaning to say that the transpose of that matrix is equal to the matrix itself, right? And this is always greater than 0 for all x belonging to the n-dimensional space, excluding the null set, right? Because if x is 0, then this inequality would not hold. So when this greater than sign is replaced by less than sign, we obtain the definition of a negative definite matrix. So both these positive definite matrices and the negative definite matrices are always non-singular matrices, and their inverses are also positive definite and negative definite respectively. So now when this greater than sign changes to either greater than or equal to or less than or equal to, then those matrices are defined as the positive semi-definite or the negative semi-definite. Okay? So this is one of the important results with respect to positive definite matrices. So the following statements are equivalent for a symmetric square matrix of dimension n, that Q is a positive definite matrix, which is equivalent to saying that all eigenvalues of that matrix are strictly positive. So if Q is negative definite, then all eigenvalues of that matrix are strictly negative, right? Which is equivalent to saying the determinants of all upper left sub matrices of Q are positive, and vice versa if the matrix is a negative definite, which is again equivalent to saying that there exists another square non-singular real valued matrix H such that the matrix Q is basically the multiplication of the transpose of that matrix with itself. Okay. Another result we have that for a positive definite matrix Q, we have, let's say this is the relationship what we have been studying. Now the minimum value of this quadratic form is given by lambda min of Q, and lambda min defines the smallest eigenvalue of the matrix Q multiplied the squared norm of the x, vector x. The largest value would be it would be less than or equal to the largest eigenvalue of the matrix Q multiplied by the squared norm of the vector x. And since we know that Q is a positive definite matrix, this would always be greater than 0. This is in fact the definition of the positive definite. So this 0 would be the lowest value. Okay. So let's consider one basic example before moving to the definitions of stability. So this is a simple pendulum what you have been seeing in your wall clocks particularly. So here in the first, so this two equations defines the basic equations of motions of a simple pendulum where the torque R balances out, where Q is the damping torque influenced by the external force U of T. Okay. Now if we are considering a special case of the heavy damping, that is B by I is this very greater than number 1, then this relationship can be simplified to this equation. Now here, since U is the external force supplied to the simple pendulum, if we consider U naught is equal to 0 and we plot the graph between the x dot as the y-axis and x as the x-axis as the variable x itself, then this is how the motion is defined, because it is a pure sinusoidal function scaled by the factor mgl by b. Okay, now if we want to determine the stability of this system, how we can do this analysis? So since it is pretty much straightforward to see that this system is a nonlinear system because of this sinusoidal function. So here we determine the stability around the steady state values. By the steady state values, we mean to say at those points where x dot is becoming 0 in this equations of motion. So if you see a close look at this picture, all these points are the points where x dot is becoming equal to 0. So we are interested in seeing the stability of these steady states or the equilibrium points. So around, let's say if we want to limit our time interval within which we want to do the analysis, let's say it is given by 0 to pi. So in this interval we have two equilibrium points, theta is equal to 0 and theta is equal to pi. In fact, the equilibrium points are over the entire axis is theta and pi, where n is from minus infinity, where n is an integer from minus infinity to infinity, and the even multiples of n basically define the 0, and the odd multiples of pi basically is given by these points, right? So let's see the motion with respect to different initial conditions. Let's say if the initial angle of this pendulum is at 0 degree, so this won't move. This will always stay here. Now if I initialize this motion of the pendulum, let's say at an angle of 45 degree, it will certainly make such kind of oscillation of smaller amplitude in the x-axis, and then finally it will settle down at theta is equal to 0. Now again, if I keep increasing to 90 degree, by it possibly it would make a larger deviation, but ultimately it would settle down at theta is equal to 0. Similarly 135, 170 up to just before 180 degree, right? Because if I initialize the pendulum at an angle of theta is equal to 180 degree, it won't stay at theta is equal to 180. It would certainly fall down and come to theta is equal to 0. Meaning to say that theta is equal to 0 is basically the point where if I initialize between, let's say 0 to 170 or 0 to just before 180 degree, it will always settle down at theta is equal to 0, but it will never settle down at theta is equal to pi. This we can also see in this figure as well, that this point is theta is equal to 0 and this point is theta is equal to pi. So if I initialize at any point just before 180 degree, the motion will always settle down in this direction. But if I initialize at 180 degree and if I see a larger interval, either it would go towards here or go towards there with respect to this point, but it would never rest down at this point. So the question arises here, among these 2 points, which point is the stable point and which point is the unstable point? Now how we can define this formally is what we are going to see the next. So in the sense of Lyapunov, we can define that a system steady state xs, for the simple pendulum we have two steady states in the interval 0 and pi, is said to be stable if for each possible region of radius epsilon, a positive epsilon, around the steady state there is an initial state x naught at t is equal to t naught falling within a radius delta, which is again a positive number, around the steady state that causes the dynamic trajectory to stay within the region. The absolute value of the difference between the x and the steady state is less than the epsilon, the given epsilon, for all times t greater than t naught. So if we want to visualize this definition, let's say consider a second order system, meaning to say having two state system x1 and x2, and we draw two circles of radius, one epsilon and another one is delta inside this epsilon. Okay, so if I initialize my system at this value x naught, which is inside this delta, then for the whole time axis, that is t tends to infinity, my trajectory will not leave this outer circle. It will always stay in this circle. Now, if you are wondering about the time axis is perpendicular to this plane. The cross-sectional view is given by here, where you are initializing at x t naught inside this inner circle, sorry. But for the whole motion, that is t tending to infinity, this trajectory would never leave the outer cylinder of radius epsilon. Okay, so this is the same phenomena which we had seen in the simple pendulum example, that if I am trying to see at the steady state axis is or theta is equal to 0, the same kind of motion I would going to see. But if I am trying to visualize this definition at theta is equal to pi, it would certainly leave out the outer cylinder with radius epsilon. Now, another definition is about the asymptotic stability, that if it is both stable in the sense we have defined in the previous slide, and in addition there exists a region of initial conditions of radius delta naught, which is again positive, around the steady state. This is the steady state point, for which the system approaches the steady state as t tends to infinity. Now this steady state could be 0 also. So like in the case of the simple pendulum, one of the steady state was 0. So basically we are finding the region of the initial conditions of radius delta naught, that if I initialize my system with with the initial condition lying in that circle, it will always reach towards to the steady state value. The last definition, the system steady state is said to be unstable, of course, when it is not stable. Let's see what do we mean by that in the sense for the linear state space system we had seen in the first week. So consider the following continuous time linear time varying system, where the linear system is given by the ABCD matrices which are time varying, and the dimension of this x, u and y are given by n, k and m respectively. Okay. So we define for this linear system that the continuous time linear time varying system is said to be marginally stable in the sense of Lyapunov, or internally stable whenever for every initial condition x naught the homogeneous state response given by this is uniformly bounded, where phi is the state transition matrix initialized at t naught, and we are seeing the response at time t. Right? It is the system is asymptotically stable again in the sense of Lyapunov, meaning to say the definition what we had seen the last slide, that whenever in addition to the above, the first point, for every initial condition x naught we have that xt tends to 0. Now here I have chosen the steady state value to be 0 at the outset as t tends to infinity. Okay. Exponentially stable, that whenever in addition there exists constant c and lambda, both are the positive scalar values, such that for every initial condition x naught the norm of the signal x of t is always less than equal to c into e to the power lambda t minus t naught, and the norm of the initial condition. So this exponential stability we have not seen in the definition earlier, but for the linear systems we know already that the response is basically an exponential response, particularly for the linear system, irrespective of whether are you in the time invariant case or the time varying case. So this is the reason we have included about the exponential stability, since the response is kind of an exponential behavior. Okay. Again, unstable when it is not marginally stable in the Lyapunov sense. So all those definitions we had seen in the last couple of slides, those definitions can be said specifically to the linear time varying system in this particular sense. So here you would see in the first point that I need to compute the response of the system, and by computing the response I need to basically compute this part, which we had already seen in the last week, which is quite difficult to compute the state transition matrix if it is a time varying case. So either I compute the solution, because if the once the solution is available to me for the time starting from the initial value to up to t tends to infinity, if the trajectory is bounded or the trajectory is reaching towards to zero, I can speak about the stability. But for that I need to compute the solution. So here we will see that without even computing the solution, how we can determine whether the system is stable or not. So one important thing to notice here is that although we have defined the system in terms of the ABCD matrices, so the rest of the matrices except the A matrix played no role in the above definition. Only the A matrix, because this matrix completely defines the state transition matrix. Therefore, in the rest of the slide, we will going to talk about the Lyapunov stability only of the homogeneous system. Because if the matrix A, which is completely defines the state transition matrix, is stable, then the BCD matrices generally played no role in determining the stability. So there are so if you try to relate those definitions with the example we had considered, that for marginally stable systems, what we are what we are interested in, that the effect of initial conditions does not grow unbounded with time, but it may grow temporarily during a transient phase. So when we were computing the response of the system start with some transients and settle down at some steady state. And the definitions what we have introduced only speaks about at the steady state. Whatever is happening at the transient state, we are not the stability in general is not concerned with that. Okay. Now for the asymptotically stable systems, the effect of initial conditions eventually disappears with time, and for unstable system the effect would grow over time depending on the value of the C matrix, that how fast and how slow it is growing. Okay. So let's see the eigenvalue conditions for the Lyapunov stability. This is in fact the first test of determining the stability, where you do not need to compute the solution of the system. So it is said already that we starting for the linear time invariant system where A matrix is no longer a time dependent. So we want to compute the stability or determine the stability without explicitly computing the solution of the system. Okay. So this is one of the important results, and possibly you have seen in your UG control course that the system homogeneous continuous time linear time invariant system is marginally stable if and only if all the eigenvalues of A have negative or zero real parts. Okay. Now if some of the eigenvalues are having the zero real parts, then those eigenvalues should be simple eigenvalues or simple roots, meaning to say there must not be more than at most one, more than one. Okay. So the system is asymptotically stable if and only if all the eigenvalues of the matrix A have strictly negative real parts. Now just to recall about computing the eigenvalues of the matrix A, let's say we have this matrix A, then you can compute the eigenvalues by lambda I minus A, where I is the identity matrix of the same dimension of what A is having, and then computing the determinant of this matrix. Then once you have the polynomial in terms of lambda, you equate it to 0, and then you compute from here all the lambdas. So all these lambdas are basically the eigenvalues of the matrix A. Okay. The third is unstable if and only if at least one eigenvalue of A has a positive real part or zero real part, but the corresponding Jordan block is larger than 1 cross 1. Again, if you have zero eigenvalues, either it could be stable or unstable. It would be stable if it is simple. If it is not simple, then it would be unstable. Okay. So here one important thing, if you want to relate it with the transfer functions, let's say we have a transfer function given by 1 by s, a simple integrator. Now for any constant input, For any constant input, you would see that the response is rising, would integrate, right? The response would integrate, and for any initial condition, the response would become constant. So what does it mean? That if I am using the integrator with respect to the initial condition, then it would be bounded, right? But it won't be asymptotically stable because the response will never go towards 0. Now let's say if I have a transfer function 1 upon s plus 1, I know that the response is exponential, and it would be in the time domain, it would be e to the power minus t. So as t tends to infinity, the response would die out. So such kind of system having these transfer functions are asymptotic stably. Now consider if we have 1 upon s square, irrespective of any initial conditions or any input, this system will always be unstable, right? So that's why we say that if we are having an eigenvalue or the roots or the poles of the transfer function at 0, then it should be a simple root. But here the roots are not simple, because here at 0 we are having two roots, or in the other sense we have Zonin blocks corresponding to eigenvalues with 0 real parts more than 1 cross 1. Okay.